Warning! The video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. In this video, we're going to be talking about discontinuity types. This is usually shoved within a section on continuity in Calculus 1 or differential calculus. And this knowing discontinuity types is kind of important as we move forward in calculus, just so that we can use common language. Not a long section, so let's just jump right into it. Definition here. A discontinuity formed when the left or right-hand limit is infinite, well, that's called an infinite discontinuity. So I'll give you an example of that here. So remember, a function's continuous if as x approaches a, the function approaches f of a. So this tells us that as x is approaching some value of a, our function is not approaching f at a, instead it's jumping off to infinity. So something like this. I'm just going to draw in a vertical asymptote here. By the way, it doesn't have to be that both the left and right hand limits are going to infinity. It just needs that one of them goes to infinity. So for example, this right here, let's say it does this or something like that. That would be an infinite discontinuity. The function's not defined at this point, x equals a. And yet, from the left and the right, one of those is an infinite limit. Therefore, this is called an infinite discontinuity. The second style of discontinuity is a removable discontinuity. So let's suppose that the limit exists, but it's just not equal to f at a. Remember, if it's continuous, then f of a would equal the limit itself. But if it doesn't, it's called a removable discontinuity. A very simple graph of something like that would be, I don't know, something like this, where you have a little hole in the graph. Notice that limit as x approaches a here from the left and the right exists, but the value at a doesn't match that. By the way, little side note, the function need not even be defined at a. Still, the limit from the left and the right exists, but yet the function's not even defined at a, so it still is considered to be a removable discontinuity because the limit exists but is not equal to the value at a, the value at a being that it does not exist. Okay, so there you go. That's called a removable, and it's kind of obvious why it's called removable, because you have removed the point from the graph. The next one is where the limit from the left and the right both exist, but just are not equal. And by the way, they both exist and are finite. That's critical. Exist and are finite, but not equal. It's called a jump discontinuity. So let's showcase what that is. Both the limit as x approaches a from the left and the right should exist. So the one-sided limits exist. So let's say that looks something like this. So the limit from the left and right are finite. They just don't match up. This is called a jump discontinuity. And I guess I should label the others while I'm here. And there you have it. All of them perfectly defined. It can be the case that during problems in your calculus course, your instructor might ask you to graph a function that has an infinite discontinuity at a point, or a removable discontinuity at a different point, and a jump discontinuity at yet another point. Now knowing kind of the looks of these types of functions, you could totally do that. This is less of a, I mean, it is calculus, but it's more of just a quick understanding type thing. But I like challenging examples, so let's take an example here. What kind of discontinuities does this function have? The function itself is e raised to the negative absolute value of cosecant of x. And I love this style of function. I like to make sure my students have come from a pre-calculus course and know how to do a lot of stuff. So how can you possibly see what kind of discontinuity this has? Graph it, and not using technology. And now you scoff and you say, how in the world can I graph that function? That's a crazy nested function, a composition of cosecant, absolute values, and e's. I can't do that. Sure you can. You could totally do that. You know how to graph each of those functions. For example, you know how to graph the cosecant. So just like you did in arithmetic, you follow the order of operations. Start with this innermost function and graph the cosecant. So let's go ahead and do that. I'm going to zoom out here and I'll quickly graph the cosecant. As you should recall, to graph the cosecant, you graph the sine first because the sine is the reciprocal of the cosecant. And then wherever the sine crosses the x-axis, you will have a vertical asymptote. So I'll just quickly kind of mark out some vertical asymptotes here. If you struggle understanding this, then you need to retake a trig course. This is very important that you know how to do this without me even saying a single word, right? This is pi, here's 2 pi, right, there's 0, x equals, negative pi and negative 2 pi. And then to graph the cosecant, you just attach to the highs and lows and you get the beautiful following graph. Notice that I'm not bothering being super accurate here. I just want to get a sketch of this. So the blue ink that you see there, so I can now erase all the black ink. The blue ink is actually the graph of the cosecant. Now I'm going to apply the absolute value to that. The absolute value just takes all the y values, this is from pre-cal, but it takes all the y values that were below the x-axis and flips them up to the above the x-axis. So it does this. And by the way, it goes on forever in both directions. I'm just not doing that. So this is the absolute value of the cosecant. Now we're going to apply the negative to that. And we know what a negative does. It just rotates about the x-axis, the function. So I'll go ahead and pause and do that. And now we've arrived at this. This would be the negative absolute value of the cosecant. And finally, we raise all those y values to base e. So let's have a conversation about that because that's the hardest part in my opinion. Now think about this. As x's, we'll just focus on, let me get my highlighter. We'll focus on this interval right here. So let me zoom in. So look at those y values. They go from negative infinity all the way up to a height of -1 and then back down to negative infinity. So let's talk about what happens to e at those values. So as e, as its argument, maybe I should say, I don't want to use x, so I'm going to say as happy face approaches negative infinity, e to the happy face, what does that approach? Well, come on. E to the hugely negative infinite number, right? So that's the same thing. Let's say e to the negative, let's say 1,000. Even though that's nowhere near negative infinity, let's just think about this. That is the same thing as 1 over e to the 1,000th power. That's a massive number in the denominator. And we've discussed early on in this course, or your calculus teacher has probably should have discussed this with you, that a finite number over a super large number tends to 0. So whenever these y values are going to negative infinity, our e to those y values is approaching 0. Nearing these vertical asymptotes, our e to the blue ink is approaching 0. Well, what happens right here? Well, that's a -1, right? You know that from just dealing with sine. You know that sine goes from -1 to 1. So that is what the apex is there, is a -1. So as x gets really close to the middle of that interval, which is pi over 2, the y values of that blue ink approach -1. And so e will approach e to the -1st. E to the -1st is basically like 1/3. So I'm going to graph in black our curve here. Remember, we're looking at e to the blue ink. Like I said, right about there, that's e to the -1/3. So I'm going to say that's a point pi over 2, comma e to the -1. I said e to the -1/3. I meant e to the -1st, which is like 1/3 roughly. And then at the edges of this interval, as x gets super duper close to 0, well, the blue ink goes to negative infinity. And as we said, as the blue ink goes to negative infinity, So this blue ink right here goes to negative infinity. E to that blue ink goes to 0. Major thing you need to know, oops, I'll write that in red actually, is that you cannot actually plug in 0, because if you try to plug in 0 into that function, cosecant of 0 does not exist. So you can't do that. You still have those issues at 0 and at pi and at 2 pi, and you get something like this. And that is repeated forever, that is the graph of e to the negative absolute value of the cosecant of x. Now the original question was, what kind of discontinuities does this function have? And you can see the limits from the left and right both exist and equal each other at each of these points, at pi, at 2 pi, at 0, at negative pi, and negative 2 pi. So it's not an infinite discontinuity. Also, if they're equal to each other, it's not a jump discontinuity. These are removable discontinuities because there are holes in the graph there. So all these are removable discontinuities. And students often freak out. They're like, oh my gosh, I'm just going to do that. They think, do I have to be able to graph like that? You should be able to actually, given time, graph like that. You definitely should be able to graph the sine, the cosecant, the absolute value of the cosecant, the negative absolute value of the cosecant. You should be able to do those quickly, just because they might appear within an exam or something like that. Your instructor would thank you for knowing that. Other than that, that's all I'm going to talk about with types of discontinuities. We're pretty much done with this very short video. So I'll get this uploaded as quickly as possible.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.